Okay, let's do lecture 22, where we'll still talk about fluids, but this time talking about hydraulics and buoyancy. So yesterday we started talking about fluids. We defined what fluids are, and then we defined properties of fluids such as density and pressure. Yesterday we learned that pressure is how much force the fluid exerts per unit area, measured in pascals. And we've learned some things about pressure, like pressure increasing with depth. So say, consider you have this fluid enclosed in this container. It could be, as we've learned yesterday, fluid can refer to either gas or liquid form. So there's fluid in here in this container, and you have a movable piston. And on top of that, you have an object with some mass. So of course, this object will exert force because of its mass. So you have a downward weight force that's exerted over this area. And so this mass will exert pressure on the fluid. Now, if you add extra weight on top of the fluid, then this extra weight is essentially extra force, will add extra pressure on the fluid. Now, Pascal's principle says that the extra pressure applied by this extra weight that you've added will be transmitted throughout the fluid undiminished. And so the amount of extra pressure exerted at this point will be the same amount of extra pressure felt by the walls of the container and felt by every part of the fluid. Okay. So that's essentially Pascal's principle. And the fact that the applied pressure is felt throughout the fluid undiminished has practical applications. For example, the Heimlich maneuver. If you apply external pressure here, the applied pressure is transmitted all throughout the body, including the windpipe, and that pushes the food out of the choking person. Or if you squeeze the end of a toothpaste tube, the external pressure you apply at the end is felt by every part of the tube, including the toothpaste inside, and that causes the toothpaste to come out. Hydraulic lifts also operate on Pascal's principle. The pressure applied, so you have this, the pressure applied over the small area A1. The pressure is force over area. So whatever force you apply here over this small area A1 gets transmitted throughout the fluid equally. Okay? And every part of the fluid will feel the same amount of extra pressure that was exerted on area A1. And that causes a force at area A2 that will lift the car here. So the pressure at area A2 will be the force divided by the area A2. And according to Pascal's principle, whatever extra pressure was exerted in A1 will be transmitted undiminished throughout the fluids, including the walls of the lift, and also including the area A2. So area A2 will also feel the same amount of extra pressure that was injected in area A1. So if we work out Pascal's principle in terms of the forces and the areas, we have this equation, and that results to a larger output force at area A2. To appreciate that the force at area A2 is indeed larger than the force at area A1, okay, let's put some numbers to visualize that. So say, for example, the ratio of area A2 to area A1 is 20, meaning area A2 is 20 times bigger than area A1. Then Pascal's principle says that the force felt by area A2 will be 20 times the force felt by area A1. So, sorry for some labeling typos there. So that will be the force exerted in area A1. Right, so through Pascal's principle, by adjusting the ratio of these areas, you're able to adjust what force is being exerted at this bigger area to achieve the force that you need. Right? Okay, so just a simple example. It's a direct application of Pascal's principle. You have baby Patrick standing on this end of the lift, hydraulic lift, mass of 40 kilograms, area A1, and you have here giant Patrick on the other end being lifted up by a smaller Patrick. Of course, it's giant Patrick is much heavier, but he's standing on a much greater area as well. What is the area A1? Right, so at area A1, you have a pressure of force 1 over area 1. At area A2, pressure of force 2 over area 2. Pascal's principle says that these pressures should be the same. And hence you have this equation relating the forces and the areas. You can rearrange this to find area A1. Okay, that's what we want, right? Be careful. What we need is force. What's given is mass. So 40 kilograms and 200 kilograms, these are masses. And so to get the force, multiply them with G. Hence you'll get the area of 4 meters squared. Relatively straightforward, I hope. Okay, yep, so Pascal's principle says a pressure applied on one part of the fluid is felt by every part of the fluid equally. So I'll show you a video that's quite interesting, which applies what we've just learned about Pascal's principle and pressure being transmitted equally. And what we've learned yesterday, where pressure depends on depth, and that the deeper you go, the higher the pressure. So, so just watch this video, and then we'll talk about pressure some more. And I hope the sound will.
Today we're going to do an experiment.
So the sound's not working, so I'll just have to just pause this. Yeah, so there you go with Pascal's barrel. You will again encounter this Gedanken experiment of the Pascal's barrel in the workshop, but it essentially demonstrates Pascal's principle and pressure increasing with depth. Right. So moving on. Buoyancy is another consequence of pressure increasing with depth. So buoyancy is defined as the apparent weight loss of an object when it's totally or partially immersed in a fluid. So let's consider here the object. It's immersed, it's totally submerged here, in this case, in a fluid. So we know that this object will feel pressure because of the water surrounding it. But we've learned that the pressure will change with depth. The deeper you go, the higher the pressure will be. So at the bottom, you have a higher pressure, and above the object, you have a lower pressure. And we learned that pressure is equal to force over area. So that means that above the object, there will be a smaller force compared to that below the object. Okay, so higher pressure below the object due to the deeper depth of water will create this larger force below the object. Okay. So we have these two forces, one downward and one upward. The net force will therefore be upwards, and that net force is what we call the buoyant force, FB. Right. So the buoyant force is exerted by the fluid on the object that's submerged in the fluid. Let's derive an equation for this buoyant force. We know that the pressure exerted by the fluid is equal to force divided by area. If we work this out to isolate the force, that will be pressure times area. But we know that pressure depends on depth, and hence the force will also depend on depth. Right, so rho, the density of the fluid, times G times H, H giving you the depth within the fluid. Now H times A, these are dimensions. H is height and A is area. So in short, H times A is equal to volume. Therefore, the buoyancy force will be equal to the density of the fluid times G, 9.8 meters per second squared, times the volume of the fluid. Or alternatively, if you use the definition for density being mass over volume, then density times volume is equal to mass, right? And therefore buoyancy force is also equal to mass of the fluid times G, which of course we know as the weight of the fluid. But what is this weight of the fluids? Archimedes was the one who stated this relationship, saying that when an object is fully or partially submerged in a fluid, a buoyant force from the surrounding fluid will act on the object. And as we've derived, the buoyant force is always directed upwards, and the magnitude of the buoyant force is equal to the weight of the fluid displaced by the object. So the weight of the fluid displaced by the object is written down in this equation as rho times V. So rho times V, where density times volume, this is equal to the mass of the fluid. That's density of the fluid, volume of the fluid, and therefore that's the mass of the fluid. Or buoyancy force is, as Archimedes said, it's the weight of the fluid displaced, because mass times G gives you the weight. So two alternative forms for buoyancy force. You can express buoyancy force in terms of the density and the volume of the fluid displaced, or the weight of the fluid displaced. Just, oh, sorry, let me just tidy up. Yeah. All right, so we've so far talked about the buoyancy force. Okay, this buoyancy force, it's upwards, but the object also has mass, right? the object also has mass. And so anything that has mass will have weight. So this object will also have a weight force, and weight force we know is always directed downwards, and it's equal to the mass of the object times gravitational acceleration. So an object that's immersed in fluid will experience two forces. First, the buoyancy force, which is always directed upwards, and you can calculate the buoyancy force using Archimedes' equation here. And the second force that the object feels is the weight force because of its own mass. All right, so by comparing these two forces, the buoyancy force and the weight force of the object, we can then define when an object, we can define a criteria for when the object will sink, rise, or float, and hover. So when we say sink, we mean that the object accelerates downwards. When we say rise or float, it means accelerates upwards, and hover, it means it's just staying on the same level. So by comparing the forces, because there are two forces acting on the object, we know that if the buoyancy force is less than the weight of the object, such that your free body diagram looks like this, right? You have a bigger upward, sorry, this is the opposite. Apologies for that. So buoyancy force is always upwards. And of course, weight force is always downwards. All right, so if your free body diagram looks like this, then your net force will be downwards, and Newton's second law of motion says that your acceleration will be in the direction of the net force, and therefore the object will sink. If, on the other hand, the buoyancy force is greater than the object, then you have a greater force provided by the fluid supporting the object. And once again, Newton's second law of motion says that since the buoyancy force is greater than the weight force, the net force will be in the direction of the buoyancy force, and the acceleration will therefore be upwards in the direction of the buoyancy force. And when the weight force and the buoyancy force are equal, then this is when the object's in equilibrium, the net force is equal to 0, the acceleration is equal to 0, and the object's just staying in the same level. It's hovering in the same level. Right, if we write down the definition of buoyancy force and definition of weight force, so buoyancy force, as Archimedes said, it's the density of the fluid times g times the volume of the fluid displaced, and the weight of the object, which is mass times gravitational acceleration. But we write down mass in terms of density and the volume of the object. Then we have these two forms for the buoyancy force and the weight force. G is just the same, so that's the same. We'll see later on that the volumes will actually be the same. So aside from comparing the buoyancy force and the weight forces, we can compare the density of the object relative to the fluid to determine whether the object will sink, rise, or float. So it follows, therefore, that if the density of the fluid is less than the density of the object will sink. And if the density of the fluid is greater than the density of the object, then the object will float. And of course, if they have equal densities, then nothing. Then the object's just staying in the same level. It's neither sinking nor rising up. All right, so are we okay up to this point? We've defined what buoyancy force is. It's the weight of the water displaced. And so looking at this equation for buoyancy force, if we want to find what the buoyancy force is, we need to know the density of the fluid. And density is a property of the material. So you can just look this up in the table or Google searches like density of water or density of seawater. You can easily find out what's the density of the fluid. G is of course constant, so you also know what G is. So the only real problem, the only real obstacle in finding the buoyancy force is finding the volume of the fluid that's displaced by the object, right? Okay, so to find the buoyancy force, you need to find the volume of the fluid that is displaced by the object. So there are only really two scenarios. First scenario is when the object is fully submerged in the fluid. Okay, in this first scenario, when the object is fully submerged in the object, the displacement rule says that the volume of the fluid displaced by the fully submerged object is equal to the volume of the submerged object itself. Okay. Yeah, so if the object is fully submerged, if you want to find, if you can find the volume of the object, say for regular shapes, it's easy. If the volume, if the object is a cube, then just measure the dimensions, multiply all of them, then you can find the volume of the fluid displaced. If the object is not fully submerged, then the volume of the fluid displaced will be equal to the mass of the object divided by the density of the fluid. Okay. So how do we come up with this equation? This is a general equation for finding the volume of a fluid displaced by a partially submerged object, but that comes from, again, comparing the forces acting on the object. So if you have this object that's partially submerged, it will still feel a buoyancy force because the fluid is still pushing up on this object. And it will also feel the weight force because of its mass. If the object is just hovering, it's in equilibrium, the buoyancy force is equal to the weight force of the object. And if you expand buoyancy force using Archimedes' principle, then buoyancy force is equal to the density of the fluid times the volume of the fluid displaced times G. Okay. G, of course, will cancel on both sides of the equation, giving you a way to determine the volume of the fluid displaced. It's the mass of the object, which you can find by weighing, using a scale, and divided by the density of the fluid, which is a property of the fluid. Right? Okay, so let's look at an example, which is quite a classic example. We all know that if the iceberg, the saying, you're just looking at the tip of the iceberg because essentially you're just looking at a small part and there's a much bigger submerged volume. In this example, we want to find what fraction of the volume of an iceberg that's hovering or that's floating in equilibrium is visible. Right. And the iceberg is in seawater. The density of seawater is given here, and the density of ice, which essentially is the density of the iceberg, is also given here. So how do we start solving this problem? Okay, any buoyancy problem, it always goes back to the how we derive the equation for buoyancy in the first place, right? It's always going back to the forces that are acting on the object, whether it's fully or partially submerged. So we know that you always have weight force because of the object's mass, and you have the buoyancy force exerted by the fluid on the object. Okay. So this is always the starting point for buoyancy problems. The iceberg is in equilibrium. It's neither rising or sinking. So we know that the buoyancy force should be equal to the weight force of the iceberg. And this is actually the key for solving this problem. Everything else follows from this initial step. We want the volume. There's nothing telling, I mean, in this equation as it stands, there's no volume relationship. But if we expand buoyancy force using Archimedes' principle, Archimedes' principle says that the buoyancy force is equal to the weight of the fluid displaced by the object. Hence, the left-hand side of the equation will be equal to the weight of the fluid or the seawater displaced by the iceberg. Okay. Weight here, weight is mass times gravitational acceleration. Mass was written down in the form of density times volume. Okay. Right. Multiplied with G, giving you essentially the weight of the water displaced. We do the same thing on the right-hand side. The mass of the iceberg can be expressed in terms of the density of the iceberg and the volume of the iceberg. Okay. Right? G appears on both sides, so just cancel out G, giving us a relationship between volumes and densities. Just rearranging this equation above here gives you this ratio of the volumes of the fluid displaced to the volume of the iceberg and ratio of the densities. Does that make sense so far? All right. Okay, so I just copy over that same equation here, and let's relate this equation to the scenario. So the iceberg, of course, that's the total volume of the iceberg here. Now the question is, what's the volume of the fluid displaced? So it's again going back to the question of finding what's the volume of the fluid displaced. So this displacement rule says that if an object is fully submerged, the volume of the fluid displaced is equal to the volume of that object that's submerged. So therefore, the volume of the fluid displaced will be equal to the volume of the submerged iceberg. So whatever volume this is will be equal to the volume of the fluid displaced by the iceberg. Right. Going further, the question says what fraction of the iceberg is visible. So what we want is what fraction is this tiny bit compared to the whole iceberg. And so to get the fraction, we need to find how much volume this tiny bit of visible iceberg is in relation to the total volume of the iceberg. So to get the volume of this visible iceberg, we just subtract the volume of the submerged iceberg from the total volume of the iceberg, right? Okay. Right, the volume of this visible iceberg here will be the total volume minus whatever volume is submerged. So that will give you this the numerator in this fraction we're trying to solve. Divide that by the volume of the total iceberg to give you the fraction of this visible iceberg compared to the total volume of the iceberg. Yeah, displacement rule, as we've stated up here, says that the volume of the submerged object, the volume of the submerged iceberg will be equal to the volume of the fluid displaced by that submerged bit. And so we can write this fraction as this in the form of the volume of the fluid displaced by the submerged iceberg. So just changing the volume of the submerged iceberg will be the same as the volume of the fluid displaced by that submerged bit. And if we simplify this, this mathematically, we can distribute the denominator to each term in the numerator. V iceberg over V iceberg gives us 1, and V fluid displaced divided by V iceberg gives us this. Yeah. Which then, going back to the equation we've derived earlier, this whole bit can be expressed in terms of the densities, right? Volume of the fluid displaced over V iceberg is also equal to the ratio of the densities between the densities of the iceberg and the fluid. Okay. So in the end, we didn't really need to know the exact, the actual volumes of visible and submerged and total volume of the iceberg. We only needed the densities of the iceberg and the fluids to solve that only 10% of the iceberg is visible and 90% is submerged. Cool. All right. Any question about this? Because then this example shows us a general relationship that when you have an object that is submerged, then if you wanted to find the fraction of the object that's submerged, you simply get the ratio of the density of the object to the density of the fluids. Or if you want to find the fraction of the object that's visible, then you do 1 minus the volume that's submerged. And so this gives you the example we did, gives us a general relationship of finding the amount of object that's submerged or visible depending on the ratio of densities. Okay. Cool. Right. So the final concept relating to buoyancy is this concept of apparent weight. And let's look at this scenario here. You have a mass, 5 kilograms. Of course, that mass will have some weight. The weight is equal to the object's mass times gravitational acceleration. Let's just, for simplicity, assume that G is equal to 10, so that the weight is 50 newtons, as shown by a scale. This is the scale, it's 5 kilograms, giving a weight of 50 newtons. Now, if you immerse the object in a fluid, of course, that object will still have the same mass, right? It's still the same 5 kilogram mass, giving you the still the same amount of weight, 50 newtons. But then the object that's immersed in the fluid will also experience this buoyancy force that's always directed upwards. And this buoyancy force, if the weighing scale here is showing that the mass of the object is 3 kilograms instead of 5 kilograms, meaning that gives you a weight of 30 newtons, right? If you compare the real actual weight of the object in air to the weight measured by the scale when the object is immersed, there's sort of a 20 Newton difference, right, in weight. And this 20 Newton difference in weight is the buoyancy force that was exerted by the fluids on the objects. And so we call this buoyancy force also the, we call the difference in the weights in air and in fluid as the apparent weight. So apparent weight is the weight of the object in air minus the buoyancy force. This buoyancy force is, of course, equal to the weight of the fluid that is displaced by the object. And so if you have a buoyancy force of 20 newtons, then the weight of the fluid displaced by the object should also be 20 newtons, as Archimedes' principle says. Okay, are we happy with the definition for apparent weight? Let's look at an example, which is exactly how Archimedes' principle came up with his principle, okay, where the king asked him to determine whether the crown was really gold or whether the king was being tricked. So it's this experiment here. The crown has a mass of 14.7 kilograms when it's submerged in water. But when the crown is in air, it's probably the other way around. It's the other way around. In air, the weight of the mass of the crown in air is 14 kilograms, but when it's submerged in water, an accurate scale gives it a mass of 13.4 kilograms. And we want to find whether the crown is really gold, is gold or not. So the way to find this is to find the density of the crown, right? Density is a property of a material, and you can easily find out what's the density of gold. So if the crown was really gold, then the density should be 19.3 times 10 to the 3. But the question is, how do you determine the density? Well, density is equal to mass over volume of the crown. So the mass of the crown, you can determine that 14.7 kilograms. It's now a question of determining the volume of the crown, but the crown is irregularly shaped. So it's hard to measure the dimensions of the crown to determine its actual volume. Right. So the question now that Archimedes was thinking is, how do I determine the volume of the crown? And he found out that if he immersed the crown fully submerged in water, the volume of the water displaced should be equal to the volume of the crown, and that will allow him to calculate the density of the crown. Right. So this is how this problem is solved. So let's just quickly see how to solve this, right? So we know the weight of the crown in air. Okay, given the mass, just multiply that with G. And then we know the weight when it's submerged. Given again the mass of the crown when it's submerged, we can find the weight of the crown when it's submerged. The difference, so there's a difference in the weights in air and the weights in water, and that difference is the apparent weight, and therefore we can find the buoyancy force exerted by water on the crown that's submerged. Right, we know the weight in air and we know the weights in the submerged water. So the buoyancy force, we can determine 12.74 newtons. So the buoyancy force should be related to the volume of the water displaced via Archimedes principle. The buoyancy force is equal to the weight of the water displaced. The weight of the water displaced can be written down in terms of the mass times gravitational acceleration. Mass, of course, is density times volume. So therefore, we are able to find the volume of the water displaced. Okay. Right? This is the volume of the water displaced by the crown. Okay. Since the crown is fully submerged, the displacement rule says that this volume of the water displaced will be equal to the volume of the crown, which is fully submerged. And hence, right, knowing that the volume of the crown allows us to determine the density of the crown, 11.3 times 10 to the 3, or 11,000 kilograms per meter cube. Looking at some materials which has that density, the crown is actually made of lead. Okay. It's not really gold. Okay, any question about the solution here? It's it's quite tricky, but we sort of the flu. I think what's confusing sometimes is we're talking about two different volumes here. For example, here we're talking about the mass of the crown, and here it's the mass of the water displaced. And relating those two is really key to unlocking buoyancy and Archimedes principle. Right. Any questions about anything? Right, cool. And then, so that ends our discussion on buoyancy and hydraulic lifts. You encounter similar questions in the workshop, but otherwise, I wish you a good day, and I'll see you in the lecture tomorrow, where we will wrap up fluids. Last lecture on fluids, which will also be the last topic covered in the test. So have a good day, everyone.